In this video, we look at two further applications of 2x2 matrices. So first off, we have, we can actually use matrices to transform points, okay? To transform points when you write the points as column matrices. And we'll demonstrate that in a moment, but first it's worth noting the following transformations. First, if we want to reflect in the y-axis we would apply this matrix, negative 1, 0, 0, 1, and that will reflect our image in the y-axis. Similarly, if we want to reflect in the x-axis, we would apply the matrix 1, 0, 0, negative 1. And lastly, if we wanted, we can also do horizontal stretches and shrinking and vertical stretching and shrinking. To get the horizontal stretching and shrinking, we would apply the matrix K001, which kind of makes sense because this did a reflection in the y-axis, so that was some sort of a flipping over that way. Well, this tends to expand and shrink about the y-axis, so it moves things back and forth that way. So that first the top left entry is what kind of controls that, and with the rest being 0 and then 1 on the main diagonal. Similarly, for the vertical, we saw that the bottom entry controls what happens in the vertical direction. Namely, if we want to do a reflection in the x-axis, flip it that way. Or we could do a vertical stretch or shrink, and we would expect to have K in that spot, which indeed we in fact do. So for instance, let's go ahead and find the image of the square whose vertices are 0, 0. So we have here the point 0, 0. We have the point 2, 0. 1, 2. We have the point 0, 2. So that would be up here. And then we have the point 2, 2, which would be there. After a reflection in the y-axis, well, we kind of have an idea of what it should be, but let's go ahead and we expect it to be this, right? We expect it to be this. I'll write a sort of a shadow image, right? But we can find those by doing the actual transformation. Namely, we're going to write each of the points the following way. So a reflection in the y-axis is negative 1, 0, 0, 1. And we're going to apply that to each of the points. So 0, 0, 2, 0, 0, 2. And see, I write them as column matrices, like so. 0, 0, 2, 0, yeah. So negative 1, 0, 0, 1, negative 1, 0, 0, 1, negative 1, 0, 0, 1. Alright, this is one of those things that takes longer to write out than to actually do anything. Here, multiplying through, we're going to get row by column, we get 0, row. So we'll get 0 there, and then for the second one, row by column, we will get 0 again. So 0, 0 goes to 0, 0, which we kind of expected. So let me go ahead and draw this out. So this point got sent to that point, right? Now, we have here negative 1, 0, so I'll call this A, B, C, and, well, C and D. So A got sent there. Negative 1s, this was A, this will be B, this will be C, and this will be D. So here we have, through there, we're going to get a negative 2. Sorry, I don't know why I put a negative 1 there. Negative 2. and then row by column will get 0. So B got sent to -2, 0, so over to there. So that's B now. C, we'll get a 0, and then we'll get a 2. So nothing happened there. So C, well no, C got sent to itself. So yeah, nothing changed. So we have this so far. And then finally, the last vertex, we would have -2, 2. So that point got sent over to here. And so you see it does in fact actually do what we expected it to do. Now it's your turn to try an example. Find the image of the square in the last example after a vertical stretch by a factor of k = 2. On the count of 3, I'll reveal the solution. 1, 2, 3. So here we see that by transforming the points on the original square by what should give us a vertical stretch by a factor of 2, by putting a 2 down there, and the lower right entry of our transformation matrix, we end up with the following transformation, as we expected. So that was our first application of matrices. Here's another application of 2x2 matrices. If we want to find the area of a parallelogram with vertices 0, 0, A, B, C, D, and A plus C and B plus D, all we have to do is use the following formula. Which is that the area is the absolute value of the determinant of A. So this gives you a good idea of what the determinant actually represents. It really represents some sort of a parallelogram. So let's do an example of this instead. So suppose we have the following parallelogram, namely, it would be 0, 0, it'll be 2, 0, so 1, 2, right there, 2, 0, then 1, 3, 1, so 1, 1, 2, 3, and then 3, 3. So that would be over here. So we have this parallelogram, right? Well, to find the determinant of, to find the area of that, the area is going to equal just the determinant of the matrix A, B, C, D. Well, what is A and what's B and what's C and what's D? So we have 0, 0 here. This must be AB and this must be CD, because if I do A plus C, I get 3. And if I do B plus D, I also get 3. So this actually works out. And so our matrix would be A, B, C, which is 1, and D, which is 3. Right? And so it's going to be the determinant of that, so let me just write it this way. That. So that's going to be 6 minus 0. So the area is, in fact, 6. And now it's your turn to try an example, so go ahead and find the area of the following given parallelogram. On the count of 3, I'll reveal the solution. 1, 2, 3. So this is what our parallelogram looks like. I double checked to make sure that with my A and B as each 5, and my C is 2, and my D is 4, that in fact this is A plus C, comma B plus D. And thus, once I've checked that to make sure that it works, I then have the determinant of this, and absolute value is 20 minus 10. Absolute value of 10 is 10, and so 10 is my area. For more practice in working with these two applications of 2x2 matrices, be sure to see page 596 of the textbook. In our next video, we'll talk about our last application, which is usually a favorite of students, and it's actually one of my favorites as well, which is cryptography.